Okay, so thank you for this opportunity for me to talk to you about modeling in the context of thixotropic materials. And broadly speaking, this is related to the overall idea of looking at rheological response. And since you have been looking at flow of complex fluid, when we do flow in a controlled manner under controlled conditions and using viscometric flows, then we can measure rheological properties. Right. So this leads to measurement of rheological properties. So that's what is a broad sort of framework that is used to look at flow behavior in a controlled condition. The idea of models is to be able to describe this behavior and property in a more quantified manner. And so this lecture, basically what I'll do is first introduce thixotropy, and so that we can at least write down some of the basic things that are required for us to say that material is thixotropic. Then I'll discuss a very simple model which describes the rheological response of a thixotropic material using one particular property. And many of you may not be used to this quantity, but this is called a stress growth viscosity, or it's called a stress growth experiment. This is different, slightly different compared to what you're used to. When we say viscosity, generally it's a steady state property. But what we are looking at in this experiment of stress growth is how stress changes as a function of time. So stress growth viscosity also changes. So this is basically a function of time, while this viscosity is a constant, right? So therefore, it's basically only a function of maybe strain rate, but in this case, it keeps on changing, and particularly there may be a growth to the viscosity. So that's a property we will see how it changes for a simple thixotropic material. And then we will look at some broad questions in the rheological response of thixotropic materials. And based on that, then we will look at some data from our own students who have done some work related to thixotropy of slightly different systems. Basically, two different things we will talk about. One is mayonnaise, which is a food that is quite common these days in sandwiches and subs and all sort of food dishes as a condiment. And then we also have some other materials which are fumed silica suspensions. What I am writing is visible, right?
Yes, sir.
Hello?
It's visible.
Yeah,
It's visible.
Okay, yeah. And then in the end, we will end with a more complicated model, which we will call thixoelastoplastic, viscoplastic also for V. So TEVP. Elastoviscoplastic. So you can see that there is thixotropic materials may not just be thixotropic alone, but they may have features of viscoelasticity, they may have features of plasticity. So while describing thixotropy, we will see that the introductory aspect of thixotropy. And just as a reminder, when we are looking at rheology as a whole, we are looking at the following approach. We basically classify and look at the material from a specific class of response. It's not really that the material itself is, of a given type. Quite often it depends on the context and what application we have in mind. So, for example, crude oil, it's perfectly okay for us to assume it to be Newtonian in some circumstances, and in some other, when we are, let's say, discussing long distance pumping. But when we are talking about the fact that once in a while from crude oil there is a waxy crystals form, and then that will lead to clogging of the pipeline, then we are looking at, it's a yield stress material and it's a viscoelastic material. So therefore, it can be, depending on the context, we may study one or the other phenomena. So that's why we need to generally look at what class of material and in some sense, what is the qualitative description. So this is the first step that we need to do. So today, for today's lecture, we are going to focus on thixotropic materials. But we will say that see that they will also incorporate aspects of viscoelasticity in them and also yield stress in them. But our main focus will remain on thixotropic materials. And once we say that we are studying a given class of materials, the study has to be done by looking at measurement under controlled conditions. As I mentioned, this is what is rheometry. And since we are measuring something using rheometry, we can then do quantification of material response. And the quantification is done by defining several quantities. And what I mentioned on the first slide was the stress growth viscosity, which is slightly different than viscosity, which we are used to. Of course, we can define, those of you who have had some background in rheology will know that there is storage and loss modulus and or stress relaxation modulus and so on. So several such material functions can be defined. And using this, then we can analyze the response of the material. However, the understanding is not complete until we do modeling also. So generally, the first step towards doing modeling is to use a phenomenological model. We can also, of course, do a microscopic model. We can also these days do computer simulations using the computer models of whatever system we are trying to investigate. So, but for our purposes today, we will focus on phenomenological models, which implies that they are trying to describe the behavior and phenomena of the systems, and that's the main goal. And so, towards this, we will discuss this structural model, and we will see that when thixotropy is concerned, an important feature is the description of structure by using what is called a structural parameter. And so modeling will involve a hypothesis of the structural parameter and how it changes with time. Otherwise, generally, these models are basically relations between stress, strain, and strain rate, and maybe other quantities which are related to stress and strain rates. So when we have a thixotropic material, we now have to look at, of course, these quantities, but we also look at structural parameter. So we will see that a model for thixotropy will have to have the variables which are always involved in rheology and the variable which describes the structure of the material. Central to the idea of thixotropy is the fact that you have breakdown and formation of structure. So because of this breakdown formation, the structural parameter keeps on changing, and therefore we will need an equation for structural parameter also. So this is just a qualitative description of thixotropic materials. Many times they will be said that they are time-dependent materials. So because of these breakdown and rebuilding processes, there is always dependency on time. Sometimes people may refer to it, if it takes a certain amount of time for rebuilding to happen, then we will say that, oh, the material is aging. There could be an yield stress involved because for some amount of stress, the material acts more like solid and then it starts flowing more easily and acts like a fluid. So therefore, there is an yielding. And there would also be rebuilding and formation of structure, as I talked about. And so in general, what we have is it's a material with evolving structure. And more importantly, during the rheological characterization itself, the structure is evolving. And so the material response, therefore, is an intricate interplay of stress, strain, and strain rate, and also the structure that is evolving. One way to sort of relate this to a viscoelastic material. So viscoelastic material, as some of you may know, has a relaxation time which is finite. So relaxation time which is finite. By that I mean is if the relaxation time is 0, then we have a Newtonian viscous fluid. And if relaxation time is infinity, then we have a Hookean elastic solid. So, but if it's a finite value of relaxation time, then there is a relaxation in the material which happens at the finite rate, and therefore relaxation time is a very good indicator of viscoelasticity. It tells you how fast or slow the dissipation in the material is happening or relaxation in the material is happening. Now, for a thixotropic material, the relaxation processes, they change because the structure is evolving. Since there is an evolving structure, there is a change in the relaxation process. In a polymer melt or in many colloidal dispersions, if they are not thixotropic, then we can say that there will be relaxation processes, but and due to that relaxation processes, the material will have a time-dependent response. But for a thixotropic material, the time-dependent response is because the relaxation processes in the material are changing. And because of this processes are changing, the relaxation time itself is changing. So generally, again, for a polymer solution or a melt, set of relaxation times are fixed. But for a thixotropic material, they may be different based on the extent of rebuilding or extent of formation. So therefore, the structure is related to relaxation time. Relaxation time affects the relaxation process. And that's how then the stress strain and other response in the material gets modified. Now, sort of this is an old idea. It's been around, and there are several materials which actually show thixotropy. A lot of them are in our day-to-day use. Creams and pastes, waxy gel I talked about from crude oil, many pharmaceutical formulations, blood itself, because in case of blood, there is the red blood cells. They can form a structure called roulettes, and the roulettes are basically stacking of these red blood cells. And so this microstructure can evolve as a function of shearing, as a function of other conditions, and it can lead to breakdown and reformation of these roulettes. And so that's how then blood also shows you a thixotropic response. Cement paste is a very common example of thixotropic response. And going for, of course, closer in terms of food also, there are lots of food which have examples of thixotropic materials. And I spoke about mayonnaise already. So one or two examples of results of mayonnaise we will see. And not just mayonnaise, but several other materials that we use, including cheese and ketchup. They are all examples of thixotropic materials. So let's just quickly first look at as to how do we assess whether a material is thixotropic or not. And many of you would be exposed to this particular definition, where what we do is we measure viscosity of the material by doing an experiment where we measure the shear stress by varying shear rate. And we do this by a loop where we first say that we go from a 0 to some high shear rate, and then we decrease the shear rate to again 0. And generally for a Newtonian fluid, if we were to do this kind of an experiment, we would expect basically that stress will increase. So going forward, the stress may be like this, because Newtonian flow stress and strain rate are proportional to each other. So therefore, stress and shear rate will be just related to each other through a straight line. And then when we decrease the shear rate, we will again get the same, the same result back. So basically, whether it's going forward or whether it's going backward, we get exactly the same stress. The way I have drawn it, of course, it is not superimposing, but that's because of my hand not being steady. But otherwise, forward and reverse is identical. In case of a polymer solution, again, we can sort of see that going forward, there may be shear thinning, so stress may not be linear. But then when we return, again, we get the same result, right? So whether again it's going forward or whether it's coming backward, for a polymer solution also, we will get similar results. So this is for polymer solution. So now the question is, in case of thixotropic material, what happens? And as the graph is indicating here, that going forward, we get one set of results, and then coming backward, we get other set of results, resulting in a loop, so-called thixotropic loop. And given that we've already discussed that structure keeps on changing, and so this is a consequence of structure. But more importantly, we have to realize that the structure depends on the shear rate. So you can see that while going back, the viscosity is lower than while going ahead. So these are the viscosity values which are going forward, and the viscosity values while coming back are lower, right? So therefore, because we have sheared the material and now we are returning back, the material is already broken down more so, and so viscosity is lower. And of course, if we let the material sit for some time, then again do a forward loop, we will again get back the same viscosity. So this is one way to look at, and what are called measurement of a loop, which gives us thixotropic response. Within oscillatory shear, when we apply basically a strain on the material, which is sinusoidal, then we do what is called an oscillatory test. And what we do is we subject the material to low, high, and low strain. So when we subject it to low strain, again, structure will be built up or intact. So this will be a phase where a structure is intact. And then we go to a phase where, since it's high strain, the structure will break down. So in this phase, the structure will break down. And so we can look at what happens during breaking down structure. How does the storage modulus, which indicates the amount of networking, amount of interactions, the microscopic structure of the material, all of this is dependent on G prime. So therefore, G prime will change with time because we are now subjecting the material to very high strain. And then once we subject it to high strain for some time, then we again, bring it back to low strain. And so this is called a 3ITT. So basically, this is three intervals, basically three interval thixotropy test, which again is an indication of what may be breaking down and rebuilding of the structure. We can see that the structure may not completely reform, so the G prime final value that you get may not be same as the initial, and so on. So we can break down, and so at rest you may have a structure which is intact, and in this case it is saying that there is an agglomerate which is basically a sample spanning. If I go from one end of the sample, I can go to the other end, and therefore this material will have a more solid-like response. And then when I apply a shear rate, it can actually break down. And so this will be a very fluid-like response. And then if I now change from a strain rate, which is slightly lower than whatever was gamma dot 1, then again, slight reformation, rebuilding will happen. So that's how, in this case, you can see that there is a breakdown and a rebuilding that is happening. And from a modeling point of view, we will have to be able to capture these. And so this is just showing these thixotropic loops for several materials. This is a blood sample, and again, there is going forward and coming back. Different materials are there. And also, this is carbopol gel, then a gelatin gel, starch gel. So several such materials show the thixotropic response. And in all of these cases, going forward and coming backward, there are, differences in the properties. And in fact, this one is showing that what is called anti-thixotropic, because while going forward, the viscosity is lower, and while coming back, the viscosity is higher. So in this case, the shear is causing the structure to be actually built as opposed to break down. So many times when it's possible that the interaction between particles increases, they are able to collide with each other and therefore lead to agglomerations, then you can have such a behavior. So this was an introduction. So now looking at a simple model of thixotropy. So what we need is basically, as I mentioned, given that we are looking at stress, strain, and strain rate, and all these different materials, different variables for materials, they will definitely be involved in a model, but we also need structural parameter. So now when you sort of look at, so this is one example where we are now looking at a structural parameter, and we make a hypothesis that there is a scalar. Of course, depending on how we want to describe the structure, you could have, let's say, not just one parameter, but maybe a family of parameters. In which case, it's a vector, of structural parameters, each one indicating something. But in the example that I gave, this could be sort of extent of agglomeration in the material. So if the fluid is completely agglomerated, then we will say that SP tends to 1 for an agglomerated material, and SP will tend to 0 for a completely broken down material in which there are no agglomerates. So therefore, the structural parameter in a material will change. And so we can have an evolution equation to describe this structure, how it breaks and forms. And this is quite like, the forward and backward reaction and writing the overall rate. So the evolution of structural parameter will depend on, how much is the extent of rebuilding that's happening, and how much of breaking that's happening. And one crucial thing is that strain rate affects the breaking of bonds. So there is a rate constant C, which talks about, how fast or slow the bond breaking is. But in addition to C, there is also strain rate. So it's a combination of both strain rate and the rate constant, which overall determine the rate of breaking. While quite often the bond formation may be just due to Brownian motion. So these particles which have broken down, they will continue to move around because of Brownian motion, and then eventually they will lead to cluster formation or agglomerate formation because they come together. So this is basically through Brownian motion. And so quite often the bond formation may happen because of Brownian buildup. But you can also have strain rate leading to buildup, as we discussed earlier. So more complicated evolution of structure parameter is done. And I'm just showing you a simple model which can describe these things. And so if you look at what may happen for this structural parameter as a function of shear rate, what we will see is that if we have very low shear rate, then structure parameter is high, and then it will keep on decreasing because we are applying higher and higher shear rate on the material. So the shear rate basically causes the structural breakdown, and therefore structure parameter to decrease in a material. Of course, in this graph, I'm only talking about what happens to the structure parameter at steady state. But at a particular shear rate, if we apply a constant shear rate and then look at what happens to the structural parameter as a function of time. So initially we will say that, okay, the structure is formed, but as soon as we start applying the gamma naught, the structure will keep on changing, and then eventually it will become a constant value. So therefore, structure parameter changes as a function of time. It is evolving. And given that the breaking processes also depend on the shear rate, the structure parameter will be different for different values of shear rate. So now what we really need to do is to get a rheological model. And rheological model, basically, then what it means is we have to combine a model which includes stress, strain, and strain rate with this structural evolution equation. And then the hypothesis we make is the model of viscous or viscoelastic fluid. The model parameters also depend on the structure parameter. So for example, if we have a yield stress fluid, which let's say we are saying that stress is equal to yield stress plus viscosity times strain rate. So this is Bingham plastic material, and all of you would have learned about this kind of a material where the tau varies as a function of gamma dot, and this quantity is yield stress. So for a Bingham plastic, if we want to make it into a thixotropic material, then what we say is, look, the tau y and eta, they may be both dependent on structural parameter. And so depending on the state of the structure in the material, the yield stress that is exhibited by the material or the viscosity which is exhibited by the material will change. So therefore, then we can say that, look, tau in the material will be a function of time and, strain rate and all that through an equation like this. Similarly, we have another equation which is for structural parameter. So both of these together will have to be solved for us to get the overall idea of stresses in the material. Because gamma dot is also affecting structural parameter. But once structural parameter changes, it affects because tau y and eta also change. So therefore, these are simultaneous governing equations, and they have to be modeled for us to get a good idea about what the response of the material is. And so what I've done here now is to just combine this, structural parameter model for with a Maxwell model. But before really looking at, let's say, Maxwell model in simple shear, of the thixotropic Maxwell model, we can just first quickly summarize what is Maxwell model. And we will look at this experiment, which is called stress growth, where you apply a constant strain rate and measure stress as a function of time. And so since it's a first order ODE, right hand side is constant, and we have basically tau yx and first derivative of tau yx, the solution is going to be an exponential. And so if you look at eta plus as a function of, sorry, let me first plot tau yx as a function of time, then we will have basically an increasing exponential function. And the time lambda, relaxation time, will tell how fast or slow this increase will be. And so for a viscoelastic material, therefore, stress will grow and eventually reach a steady state. So now let's look at what happens in case of a material. So based on this stress, we define stress growth viscosity, which is ratio of stress to strain rate. So stress divided by shear rate, which is the definition of viscosity. Only thing is, since we are looking at this as a function of time, the viscosity is called stress growth viscosity, and it's a function of time. So eta plus for a Newtonian, for a Maxwell model, is basically an exponential function. Just to remind you that for a Newtonian fluid, we will have basically the viscosity constant. So eta plus is equal to the viscosity itself, and it doesn't depend on time. And for a Hookean solid, eta plus will keep on changing with time. Modulus times time so it will keep on increasing. And so you can see that the Maxwell model is providing us an example, which is combination. So Maxwell is a combination of Newtonian and Hookean response. So at short times, we get the Hookean response, but at long times, we get the Newtonian response. So now we have to look at what happens to thixotropic material. So the combination, as I said, so there is a stress and strain rate. So we combine the stress as a function of time and structural parameter to evolution equations, and then if we specify all these different parameters, then we can solve. And for a specific set of choices, I have solved these and given an example result, where we can see that because we are changing and applying shear on the material, the structural parameter decreases, and the viscosity, stress growth viscosity, initially increases, but then it decreases and then eventually becomes constant. So this decrease is because the structural parameter is going down. As you can see that when structural parameter is decreasing, leading to breakdown of the material, the viscosity of the material also decreases. So Maxwell model alone will show only an increase and becoming constant, but the thixotropic Maxwell model will show this increase and decrease in viscosity. So this is one simple example of what the thixotropic response is of a material. What I'll do is I'll right now skip the broad questions in thixotropic response, because some of these are also related to the overall ideas that are there and how we relate thixotropic materials in terms of defining steady state, equilibrium, and some of these are also quite tricky in terms of how do we define many of these states of these thixotropic materials. Also, how do we distinguish between thixotropy and viscoelasticity and other features? Because sometimes the rheological signatures may be identical. So therefore, rather than now looking at these broad questions, I'll skip and maybe first show example data and the model itself. And towards the end, if there is some time, maybe I'll come back to some of these broader questions. So let me just skip now some of the slides, and I will come back to them if need be later on. So let me spend some time now on some example data which is generated in our own group, which is trying to look at thixotropy of two different materials, as I mentioned, mayonnaise and fumed silica suspensions. And so mayonnaise, of course, is a very common material these days. And it's a aqueous dispersion. There is oil, there is vinegar, so it's fairly complex in terms of its composition. And if we look at from a food formulation point of view, each of them, whether it's oil, egg yolk, vinegar, or any substitute of egg yolk, if it's a eggless mayo, mustard, and charged carbohydrate like CMC, which are thickening agent and also interaction. So each of them is supposed to have some specific role to play for us to give the final function out of the mayonnaise. And so the question is, how do we understand its thixotropic response? And from a point of view of thixotropy, day to day, we also see this, that when we try to spread mayonnaise on a piece of bread or any other, while making a sandwich, it spreads fairly easily. And during this process, basically, we are breaking the structure down. But as soon as we leave the thing, it rebuilds quickly and it doesn't sort of keep on flowing, right? So it's very crucial. This behavior, this thixotropy of mayonnaise is quite crucial in its overall function. And so if you look at its measurement of, up and down, so you can see that there are two sets of data. So while measuring, up and down, we can see there is a small difference in the viscosity. So this is also shear stress as a function of shear rate. You can see that there is 5 orders of magnitude change in shear rate. And while looking at food and various other materials, it's also important to study these very different shear rates. Shear rates of 100 and all those may be important when we are using a spoon to spread. But when we leave the material, then these low strain rates may be important. So we have basically a built-up structure to a broken down structure as we go from low shear rates to high shear rates. And so in terms of this material, we can see that there is a small thixotropic loop. It is not as magnified as some other materials that we have seen, but that's partly because the structure build-up processes are quite fast here. And so the 3-year interval thixotropy test also that I talked about, which is in literature, is also referred to as this 3ITT because of the interval and thixotropy test. So this is done quite often, and you can see that at 1 so this is low strain. As I mentioned, first we apply low strain, then we apply high strain, and then again we apply low strain. And of course, these graphs are also showing the model itself. And since I've already mentioned this thixotropic, elastic, viscoplastic, so what we will see is the model has to incorporate all these features for us to be able to capture. And though the steady states, the eventual values of G prime is being captured, but you can see that the transition may not be as well captured by the current state of models. And that's something which are finer points, which those of you who are interested can have an offline discussion with me related to what is the state of modeling for these kind of material systems. And one of the important things that sometimes the people try to quantify is what happens to the after, let's say, 30 seconds of recovery, how much G prime it is reached and how much it is compared to the initial. So this is the initial value, and then we from here we can get an idea of recovered value, because in between the material was subjected to a very high strain rate. So given the high strain at which the material was deformed, whatever is the droplet structure, the agglomerated droplets, the shape of the drops, all of these will keep on, getting deformed. And so therefore, the material shows a thixotropic response in terms of structural breakdown and rebuilding. So this is an example using mayonnaise. And the other systems that we have worked quite a bit are suspension systems. And these are basically fumed silica particles. And they are in two different medium. In one case, they are in polyethylene melt. And the other case, it's a paraffin oil as a solvent, or as a low viscosity medium. And a small amount of polymer is added, which can help in bridging the particles and also increasing the viscosity and so on. So in this case, the both of these cases, in one case we just sort of use stirring to make the suspensions. In the other case, we use a specific because it's a melt material. We have to use a plastic order which can mix particles with polymer melts. So polyethylene pellets will have to be fed to the plastic corder along with the fumed silica, and then we get the fumed silica polyethylene melt as an output, which is well mixed. And so given that we are interested in rebuilding and formation of structure in, we saw that there is a thixotropic loop which is examined, right? So we said that there is stress, there is strain rate, and then while going forward, we may get one value of viscosity, and while coming back, we may get another value of viscosity. So therefore, this difference in them is due to the thixotropic loop. And so one way to study this little more carefully and also look at what is happening as a function of time. An experiment that can be done is what is called a step-up experiment, where a constant value of strain rate is applied for some amount of time. Then at a given instant of time, you suddenly change the strain rate to a higher value. So that's why it's called a step-up, where there is gamma dot 1 and gamma dot 2, and gamma dot 2 is greater than gamma dot 1. And so what you can see here is basically, if you look at from the point of view of structural parameter, you would expect that structural parameter will be higher because, this is a low strain rate, and structural parameter here will be lower. So as we are doing this step change in strain rate, the structural parameter itself also changes. And as a result of this, the stress will also change. So when we do this step increase in strain rate, we can monitor stress as a function of time. And for a Newtonian fluid, it's quite straightforward, because the Newtonian fluid, the stress depends only on strain rate itself. So I hope all of you can see that initially there will be a low stress, and then there will be a very high stress. And this is the way it will be for a Newtonian fluid stress. It will completely mimic whatever is the strain rate. So stress for a Newtonian fluid will initially be constant, then suddenly it will increase, and then it will remain again constant. And so, but what about for a thixotropic material? What about for a viscoelastic material? So, as we discussed, so if you have a strain rate changing from a low value to a very high value, for a Newtonian fluid, we will see again a step change. If it's a solid material with perfect Hookean elasticity, then because strain rate is constant, strain will continue to increase. And since strain continues to increase, the stress will also continue to increase. But since the rates are different before and after, so you have the rate of increase slightly different. So the slopes are different in the two cases. But otherwise, qualitatively, the linear increase in stress is there for a Hookean solid in both the cases. But these are of course ideal materials. For a realistic material, what you have is the fact for a viscoelastic material, because of relaxation in the material, stress grows, but it takes some finite amount of time before it grows, because in terms of the overall rate being higher, the overall stress that is required is also higher. So that's true for Newtonian fluid also, but in this case, there is an evolution, and the evolution rate will depend on relaxation time. But in case of a thixotropic material, there will be a decrease. And so for a thixotropic material, because the structure is breaking down because of this higher shear rate that is there, the overall stress will decrease. So you can see that if you do this step up, step down experiment, you might be able to, see the features of viscoelasticity as well as features of thixotropy. So if you see an increase in becoming constant, the viscoelasticity. If you see a decrease in becoming constant, then it's thixotropy. And naturally, we shouldn't be surprised if we obtain a result where a constant value, there is an increase and then decrease and then becoming constant. So therefore, this is nothing but thixo and viscoelasticity both. So that's why this is thixotropic response and elasto and viscous. So similar thought process can be used for step down, but I'll skip that. And and I'll show you also results which are for step up and step down. And this is what you can see, that when a step down is concerned, then you have an increase and decrease, and this is different for two different material systems. So the increase and decrease is quite prominent in case of the polyethylene, but it is only possible to be seen in some cases if we use paraffin oil suspension. So therefore, we propose this as a new model system which can highlight the influence of thixotropy and viscoelasticity much more by changing the model system. Instead of using paraffin oil as the medium, we use polyethylene melt as the medium. So I'll close now in the last few minutes by just talking about what are the constituents of a model which can pick up all of these behavior. I also skipped through, but so we need to be able to capture a thixotropic loop. We need to be able to capture the step up and step down type of results. We also to be able to capture the three interval thixotropy test, where this is oscillatory shear. And I didn't talk about it, but we've also been able to talk about normal stress difference in these materials. And so not many reports are there since the behavior of these materials is quite complex. So measurement of normal stresses in these is also quite tricky, but we've been able to do some of these measurements, and we've been also able to model. So the model needs to be a three-dimensional model so that it can also naturally pick up normal stress differences. The Maxwell model that I showed you earlier, I only showed a one-dimensional model. So given that we are subjecting the material to shear stress and shearing, but in the material there will also be the normal stresses that are present. And so normal stresses 3 tau xx, tau yy, and tau zz in the material will also be present. And their differences is what is being captured when we are trying to look at, and this is all due to the elasticity in the material. So normal stress differences are a very good indicator of the importance of elasticity in the material. So when we are looking at a thixotropic material like what we have studied, we see that viscoelasticity and thixotropy are both together. And so we can measure loop, we can measure step up, step down, we can measure 3ITT, and we can also look at normal stress differences. And so the model basically, again, like what I mentioned in terms of a Bingham plastic or a Maxwell model, in now what we are referring to this is the structural parameter. So there is a slight change in notation now. What I had used as SP is this structure parameter. And we say that stress tensor, because now we need a 3D model. So stress is related to medium stress, and this is Newtonian. So that's why this is a tensorial representation of saying stress is proportional to strain rate, and proportionality constant is viscosity, which is the medium viscosity. And then we also have the, due to structure, which is agglomerated and all that, there is a contribution coming from the stress. And this structure, of course, also depends on the structural parameter. So this is structure contribution to stress, and there is a medium contribution to stress. So this is the way the hypothesis is, and we can see that stress is already being made a function of structural parameter. So like earlier I said, we needed an equation for dSP by dt. For these models, we will need an equation of d lambda by dt. And so this is one component along with the evolution equation of the structural parameter that we can look at. Now there are several other sort of assumptions that are also built in. And so the strain rate tensor, which is basically 3D version of gamma dot that I have been talking about, because there are three directions of velocity and the three direction in which velocity gradient can happen. So 3 into 3, 9 components, and then the symmetric part of that is what is called strain rate. So there are 9 components of strain rate, but it's a symmetric tensor, so there are 6. So in any case, the strain rate tensor is split in 2 parts. One which sort of gives you overall structural contribution, and it is called the elastic. And this is a model which is called neo-Hookean. So if you read a little bit, it's basically for a network system. So given that the particles are forming agglomerate and network, so we get a neo-Hookean solid-like response from part of the system. And then the other part of the system is viscoplastic, and that depends on what is the overall value of stress in the material. So if stress is low, then in fact there will be no deformation. There is no viscoplastic deformation. D will be 0. Otherwise, there is deformation in the material, and that depends on what is the amount of stress which is being imposed on the material. So in addition to having the overall stress being reflected, we also need these additional relations to describe the overall material response. And this is what the final equation looks like. But in addition to this, we will also need an evolution equation for dt. And of course, these are, 6 equations because 9 components of a tensor, but since it's symmetric, there are only 6 independent components. For a viscometric situation, we have only 4 components, so 4 equations. So 4 equations have to be solved simultaneously along with the 5th equation of d lambda by dt for us to get an solution. So with that, now I'll stop here. Basically, what I tried to tell you was related to the thixotropic materials and how they are modeled. And the discussion that I did, in addition to it being introductory nature, it is also based on these publications where in one we are looking at normal stress differences. In one we are looking at, how is the mayonnaise can be studied as a thixotropic property. And then a new thixotropic model with respect to, polyethylene melt. And finally, also looking at oscillatory response. So trying to do oscillatory testing of the thixotropic materials and then gauging what their overall response is. So with that, I'll stop here. If there are any questions, please feel free to ask any questions.